there. Okay, last week sort of served as a bit of a sort of introduction, sort of what PDEs are. We looked at the three different types: elliptic, parabolic, and hyperbolic. And we also looked at range of influence and domain of dependence. That was all sort of theory. I didn't notice last week, I didn't say, okay, how do we solve these things? This week, I'm going to introduce the idea of finite difference approximations. You've probably seen them before, both in previous years, and if you do also ODEs, I think Leader talked about finite differences last week. Okay, so finite difference approximations, just got to remind myself where it is in your notes. Is it chapter 2? Yeah, chapter 2. I'll be working through pretty much most of chapter 2 today, and next week I'll be finishing it off. Okay. So, I could use my new little clicker thing. Okay, so just a little background. Finite difference methods, often abbreviated to FDM. What this does is it solves PDEs by approximating the solution at various different discrete points in the domain. Okay, remember the domain is all those values of the independent variable which the PDE applies to. So a finite difference method takes discrete points. So it takes like a sample of the domain and solves the PDE at those points. Okay, what we do is we derive finite difference approximations to partial derivatives. Okay, so we approximate partial derivatives using what are called finite differences. And these are all derived from the Taylor series. And essentially, it's quite simple. We simply plug the finite differences, or we replace the partial derivatives with finite differences. And what this does, it creates a system of algebraic equations. Okay, so we actually end up with an algebraic form for our solution for our PDE, not the PDE form. Okay, so we're turning a PDE, a differential equation, into an algebraic equation. We could solve algebraic equations quite simply. That's what we do with the finite difference method. And by solving our algebraic equations, we have an approximation of the solution to the PDE. So it's all about converting or writing the PDE as a system of algebraic equations. Okay, so what I'm going to talk about today are these finite difference approximations and how these are derived and how we can use them. Okay, so you've probably seen this quite a bit, especially also if you do ODEs. If you don't do ODEs, you saw this in the first and second year. The Taylor series is kind of where all numerical methods sort of come from. Okay, the Taylor series, okay, this thing here is a summation. It's a series summation. Okay, so we have a summation, goes from n equals 0 to infinity of h to the power n over n factorial multiplied by a partial derivative of our function u. So just remember from last week, u was our function. U is the solution. Okay. What we do here is we step a short distance away from x. Okay. We want to solve at x. Okay. But we step away a short distance from x, and that's what h is. H is some small step away from x. Okay. So this series expansion, u to the subscript n, means the nth partial derivative of u with respect to x. So if I was to write that out, when n equals 0, I've got 0 to the h to the power 0, which is always 1, multiplied by the 0th derivative of u, and of course that's just u. Second term, okay, we'll get h to the power of 1 over 1, so that's h, multiplied by the first partial derivative of u. Okay, when n is 2, h to the power 2 over 2 factorial, and the second partial derivative, etc., etc. So I could go on forever. I can go on forever, summing those terms, and I will get exactly that. Okay. So that's what's known as the Taylor series. Sometimes it's expressed in a different form. If you go on Wikipedia and look at Taylor series, it's expressed in a slightly different form. But this is the form which is most useful for us. Okay, so u is some function of x, h is some small value known as step length. In this lecture today, we're also going to need what's called the backwards Taylor series. In the backwards Taylor series, instead of taking a step to the right, i.e. adding h, we take a step to the left and we subtract h. So what we do here is wherever we see an h in this Taylor series, we replace it by minus h. Okay, that's not too difficult. All that means is wherever we got an odd power of h, we got a minus here. Wherever we've got an even power of h, we've got a plus. Okay, because minus h squared is simply plus h squared. Okay, so this gives us this sort of minus 1 to the power n. That sort of alternates between plus, minus, as n goes from 0, 1, 2, etc. Okay, so this is known as a backwards Taylor series. And we'll also be needing that when we come to derive finite differences. Yes, well spotted. Deliberate mistake there, just seeing if you're paying attention. Yeah, that should be h squared. And that should be h n. Didn't spot that one, did you? Ah, you see. Yeah. Okay. Right, so if we were to sum the Taylor series over an infinite number of terms, we'd get the exact value of u x plus h. We can't do that. It's impossible. Okay, so we have to call it a day sometime. So what we do is we can truncate the Taylor series. So we ignore some higher order terms. Okay, we can do this. If you think about it, the nth term is multiplied by h to the power n over n factorial. Now, we always assume h is some small step. Okay, so for example, if h is 0.1, now in practical terms, 0.1 is actually quite large for a step length. But for the sake of argument, let's say h is 0.1. Okay, first coefficient, 0.1 to the power 0 over 0, well, that's just 1. The second term would be multiplied by 0.1 to the power 1 over 1, which is 0.1. The third term would be 0.1 to the power 2 over 2 factorial, which is 0.005. Okay, third term, 0.1 to the power 3 over 3 factorial. And we're starting to get to quite small numbers here. So after 5 terms, what have we got there? We've got 0.0000416 recurring. So it doesn't take long before we're up to really, really small terms. So higher order terms have a less of an effect on the value than lower order terms. So this is our justification for truncating the Taylor series. However, saying that, the more terms we sum to, the more accurate the series approximation. So with numerical methods, you have this trade-off between accuracy and how long you want to spend calculating these things. Okay, so that's the trade-off. Right, so here's an example. What I've done here is I've looked at a Taylor series approximation of e to the x. So Taylor series e to the x about the point x equals 0. So about that point there, that's in the region near to x equals 0, we should have, we're looking for a good approximation of this red line. So this red line here is e to the x. This blue line is the 0th order approximation using the Taylor series. So if you use a Taylor series, okay, so the 0th order approximation is simply 1. So that's a horizontal line, passes the vertical axis at 1. Okay, that's not particularly exciting, so we'll move on. First order approximation. This is a linear line. Okay, first order polynomial function is just going to be a straight line. So again, the red line is the e to the x. The blue line is our first order approximation of e to the x. So this is given by the function 1 plus x. So you can see it's slightly better in the region around this point. Okay, we've got a slightly better agreement, as we get further away from x equals 0, we're starting to see a deviation from the solution. Quadratic, okay, second order. So remember, quadratic equation looks like a parabola. Okay, so instead of the 1 plus x, now we've got a half plus x, half times x squared. Okay, and we got better agreement. So instead of the straight line, we have a better agreement. It sort of follows a curve. But down here, we're starting to see a bit of a deviation away. Okay, and finally, third order. That's as far as I'm going to. So, okay, third order approximation. As you can see, it follows pretty much on this scale all the way up, and we're starting to see a bit of deviation down there. So if I just cycle through those again, the higher the order, the closer and closer I'm getting to that e to the x. Okay, so in other words, the more terms you have in your Taylor series expansion, the closer you get to what you're trying to approximate. Okay, at the end of the day, what we are doing is we're not actually solving PDEs, we're approximating them. Okay, PDEs in most cases are impossible to solve. You can't solve them analytically. Okay, hence the need for a numerical method. But a numerical method never actually solves the PDE, only ever approximates it. So therefore, we need to know how close our approximation is. So we've always got to be aware that there is some error in what we're doing. So this is where we come in the idea of big O notation. Okay, so truncation error and big O notation. When we have our Taylor series, we truncate it. Let's say we truncate it to second order, so third order terms and higher are ignored. The ignoring of those terms is going to cause an error, and this is what we call the truncation error. So any higher order terms which are ignored are accounted for by the truncation error. We don't know what this truncation error is. We can't have a specific value because we don't know what our solution to our PDE is. Okay, so it's impossible to say, right, the truncation is this. But we can determine the behavior of the truncation error. So we don't know the value, we can analyze its behavior. And what's important is, what is the behavior of the truncation error as our step tends to 0? Okay. If our step was 0, we'd have an infinite number of discrete points in the domain. We'd actually have the solution. But we can't do that. It's impossible. So we try and have our step length h to be as small as possible. A smaller step length means a better approximation. Okay, so what we do is we express a truncation order in big O notation. This is simply a capital letter O, and in the brackets is h to the power n. So that's a function of our step length. Okay, so big O notation is a big O there, h to the power n. What this means is that for some constant c, our truncation error will behave like the function h to the n. Okay. So in other words, the truncation error will go to 0 as h tends to 0, proportional to h to the n. So what do I mean by that? Well, let's say if I got a truncation error of order h squared. Okay, halving h will reduce the truncation error by a quarter. Okay, sin h squared is 1/4. If I halve it again, it will instead of being a quarter of the original h, it will be 1/8 of the original h. So it's a behavior. It's what we call convergence behavior. Is it linear? Is it quadratic? Is it cubic? And this is given by this big O notation here. Okay. So try and sort of get it right in your own mind, but we can't ever actually calculate the solution to these things. We approximate it, and we also trying to say, okay, how close is our approximation? What would happen if I halved my step length? So I've got a solution, I've calculated the solution. What would happen if I reduced my step length? And this gives us some sort of clue. Later on in the term, we'll have methods to say, well, is it worth halving the step length? Is it worth going to all that extra trouble for a bit more extra accuracy? And we'll do that later on in the term. Okay, so what we tend to do is to account for the higher order terms, we write our Taylor series up to a given term. Okay, this is the nth term. I don't know where that is. That could be 4th, 5th, or something. And then we stick on this order h, and it's the n+1. So it's always the order of the last term that we've written down plus 1. Okay, and I want you just to note a couple of properties of order hn. If I divide order hn by h, I get order hn minus 1. So that's using properties of powers. If I have some scalar, some number, and I multiply order h to the n by that number, it doesn't change it. Okay, it's still the behavior of the error as h tends to 0 is still the same. Okay, so I can multiply it by k, and it makes no difference. Okay, we're not interested in what the actual value is. We're interested in what happens as h gets smaller. Okay, so that's the Taylor series and the truncation error. What we're going to look at now, and this is most of today's session, is deriving these finite differences. Okay, so finite differences, what we do is we truncate our Taylor series to a required order of accuracy. Okay, so I might as well start at 1, first order. Okay, so what I do is truncate the Taylor series to first order. Okay, so I've included the 0th order term, I've included the first order term, and I've truncated second order and above. So I've taken that into account with the order h squared there. Okay, so this is my Taylor series. What I can do, I can rearrange this to make the derivative of x, derivative of u, sorry, the subject. So simple algebra gives me this. Okay, note, but the order h squared has been divided throughout by h. Okay, I've divided throughout by h, so therefore, instead of order h squared, we've got order h. Okay, this is what's known as the first order forward difference. Okay, it's called forward because what we do is we step forward along the number line from x. So we calculate the value of our function u at x plus h, then we subtract the value of the function u at x, and then divide it by the step length h. So that's stepping forward forward in space, so we call it the first order forward difference approximation. We could do the same with the backwards Taylor series. So the backwards Taylor series is exactly the same, except for this sign there would be a negative. So if we rearrange that, okay, oh, and this will be a minus h as opposed to a plus h. We rearrange that, we get this. Notice, again, it's first order. Okay, so as h tends to 0, the error tends to 0 in a linear fashion. Okay, this is called backwards because we start at x and we subtract the value to the left. So it's called the backwards Taylor series. Backwards finite difference approximation. Okay, so those are both first order. Forward difference, backwards difference. Both the same order of accuracy. So they shouldn't, their behavior of the error is pretty much the same. The error might not be the same, but the behavior, the convergence behavior will be the same. Okay, that's first order. Pretty naff, to be honest. I'll show you in a minute why it's pretty naff. So the next logical step is to look at second order. So let's try and derive a more accurate finite difference approximation. In doing so, what we need is second order Taylor series. So here I've included the second order term, and I've truncated terms of order 3 and above. And I've done the same with the backwards Taylor series. Okay, so remember, instead of x plus h, we've got x minus h. So on the odd order terms, we have a minus, but on the even order terms, we have a plus. Okay, so I've labeled them 1 and 2, those equations. If I subtract equation 2 from equation 1, okay, so on the left-hand side, I've got ux plus h minus ux minus h. Ux's, they cancel out, so we're just subtracting those. For this term, we got h times the derivative of u minus h times the derivative of u. So we've got 2h. Okay, so that's where that 2h comes from. And we got some, the order term, the truncation error stays the same. Okay, even though I would have subtracted these two, there are still higher order terms there, so it stays the same. Therefore, if we rearrange this to make ux the subject, or the derivative of u with respect to x the subject, you get this. Okay. Note, this is of order h squared. Okay. So this is called the central difference because we step one node to the right, and we subtract that one node to the left. So it's kind of symmetric about the ux node. It's called a central difference approximation. This is second order. The ones on the previous slide were first order. Okay, so this should be more accurate. And we'll see in a minute, but it is indeed so. Okay, so this is a forward difference approximation. The black line is some function. I think it's some exponential function, but I can't remember. It doesn't really matter. So the black line is some function. What I want to do is I want to approximate the derivative at this point. And I've called it xi. So this is the point I want to approximate the derivative. The blue line is the tangent. So the blue line represents the actual derivative at that point. Okay. The red line is the approximation. So if this red line lies on the blue line or near it, I've got a good approximation. So the forward difference, what we do is we take a step to the right at some discrete point. So this is my x plus h. Okay, calculate the value of that function u at that point. Okay, and if I calculate the gradient or draw a line going through those 2 points, I get the red line. And this is a first order approximation, so you can see the red line doesn't have the same gradient as the blue line. Pretty naff approximation, to be honest. That's the forward difference. Backward difference, similar, except for instead of going one step to the right, I've gone one step to the left. So that's where my point is, one step to the left. Draw a red line going through those 2 points, and you can see it still doesn't have the same gradient as that blue line. So both this one and the previous one are both first order. Okay. If I look at the second order one, okay, you can see straight away it's much better. Second order difference, we take a step to the right, calculate that point there, take a step to the left, calculate that point there, and if I draw the red line through those 2 points, I have a similar gradient to the blue line. So that's a graphical explanation of the difference between first and second order. Okay, so first order ones are forward and backward. Central is a second order method. The second order approximation, sorry. What about higher order differences? Well, there are 2 ways I'm going to show you in which we can derive higher order differences. First way is using lower order differences. So we know forward, backward, and central difference. What if I want to approximate a second order derivative? Well, one way is to recognize a second order derivative is just a first order derivative of a first order derivative. So that's what we got here. So the bit in brackets, that's our first order derivative of u. And if I differentiate that again, I've got a second order derivative. Okay, so we could do the same with differences. So what I've got here is I'm saying my second order difference, so I should say a difference approximation of a second order derivative. Okay, I'm not saying what the order of accuracy is yet, but okay, my approximation of the second order difference is I've used the first order forward here, so I've gone forward in u with a difference of x. Okay, so what I've done here is I've written down the first order forward, but I've included the derivative term. Okay, so I'm going to calculate whatever the value is of this derivative term at a point just to the right, and I'm going to calculate the derivative term at x. And that is divided by our step length h. So there's a subtle thing here. Note that we're actually dealing with derivatives here. What I can do with that is I can replace those derivatives by essential difference formulae. Okay, that's what I've done here. So, sorry, I've replaced them by backward difference formulae. So here, I've got a difference about the point x plus h. Okay, the backwards difference took x and the point to the left, x minus h. So if my x was x plus h, I take x to be x plus h, and then one step to the left of x plus h, which is just x. Okay, so this is combining forward and backward. This is a forward difference, and I've put in two backwards differences in the square bracket. Okay, this one here, okay, I want the difference, first order difference about the point x, and if I'm using backward differences, I take x and then subtract the point to the left. Okay, so this should give me an approximation of my second order derivative. Tidy it up, this is what we get. So we have a minus x minus h there. We've got minus u of x minus ux there, so that gives us minus 2ux. And here we just got plus ux plus h, so that's one there. That's all divided by h squared, because I've got a common factor of h on the bottom here, multiplied by that h. Okay, that's our second order symmetric difference. Okay, we call that a second order symmetric difference approximation of that derivative. Okay, so that's one way to derive higher order differences, or differences of higher order derivatives. Okay, this is the example. I think this is in your notes. Okay, further example. What about third order? Okay, you're starting to get a bit tricky now. So a third order, what we can do is we can apply essential difference approximation to two approximations of the second order derivative. Okay. In other words, if I've got a second order derivative, which I've got on the previous slide, so if I've got this, okay, if I just take a first order derivative of that, I'll get a third order. Okay, so what do we get? Okay, a first order essential is 1 to the right minus 1 to the left divided by 2h. So I've gone 1 to the right minus 1 to the left divided by 2h. But remember, these are on their own second order differences. So I've got to replace these with that on the previous slide. Okay, comes out quite large, but this is my x for the first one, x plus h. I've got x plus h. This is a step to the left. That's a step to the right. So instead of x plus h, I've got x plus 2h. So I've gone another step. Okay, what about that one? Okay, here I've got x minus h in the middle, step to the left. So I've got x minus 2h, and a step to the right, which would be ux. Okay. If I simplify all of that down, some terms cancel out. If I take all the h terms outside, we end up with this. Okay. Rather horrible sort of looking thing. But this is an approximation. This is a second order approximation of a third order derivative. Okay. A couple of things to note about this one. We need values of 4 different nodes. 2 to the left. Okay, so that's a left-hand neighbor, and that's the one to the left of that. And that's the right-hand neighbor, and that's to the right of that. So we need 2 values from 2 steps either side of our ux. Okay. In general, an nth order difference, so a difference of an nth order derivative requires at least 2n minus 1 nodes. Okay, so this is a third order derivative. So if n is 3, 2n minus 1 is 5. So we've got 2 to the left, 2 to the right, and the 1 in the middle. However, sometimes some nodes may have a coefficient of 0. Okay, so in this case, the ux, this ux here got cancelled out there, so it's 0. But sometimes that won't be the case. Okay, what about mixed derivatives? Okay, so what if we got a derivative, first order derivative in terms of y, and then second order, first order derivative in terms of x? So this sort of thing here. Okay, so the function u is differentiated with respect to y and with respect to x. What you can do is first differentiate it with respect to y, and then whatever you get from this, differentiate it with respect to x. So what I've got here is I've got a function. U is a function of two variables, x and y. Okay, so if I first find the outer one is the difference in terms of x. So if I use a central difference, we got 1 to the right minus 1 to the left divided by 2 delta x. Delta x is my step length. That's h. But because I've got two variables, I'm going to have to in order to tell the difference between the two step lengths, I'm going to call them delta x and delta y. Okay, so 1 to the left and 1 to the right. Notice the y variable remains the same. Okay, I'm not differentiated with respect to y at all. That's just purely differentiating with respect to x. Once I've got that, I have to calculate this y derivative. And in doing so, I use a central difference. Okay, so what we got here? So this one here, okay, I take a step above y, which is y plus delta y, minus a step below, so that's y minus delta y. And that is over 2 delta y. Okay, so that's using the central difference approximation in the y direction as opposed to the x direction. And if I do the same for the second one, I've got this down here. Okay, so if I do some tidying up of the algebra, that's what we get. So we've got 1 over 4 delta x times delta y. So that's if I multiply all the bottom together. And you've got essentially the corners. So, slight typo error there. That should be, I don't know what's happened there, but it should be okay in your notes. So essentially you've got the 4 corners. Okay, so you can derive mixed derivatives using this method as well. Okay, so you start building up. If you wanted a 4th order derivative, I'm just going to go back a slide. We could do this, a first order. What's this? First order applied to this one. You get a 4th order. Okay, there is a better way of deriving it than that, though. Okay, that's mixed derivatives. That's yeah, and that's deriving it using lower order derivatives. Okay, well, that's all very well and good, but not very general. The better method for deriving them is what's called undetermined coefficients. Okay, and this will work for any order. Any order you want, this will work. And this also allows us to do sort of nifty things with skewed differences. Okay, we don't always have to have them being symmetric. We can have them one-sided. Okay, and it's a 5-step process for undetermined coefficients. What we do is we start off by writing the finite difference using neighboring nodes multiplied by a coefficient. Now, the coefficient in this case is alpha. So I've got some derivative here. Notice it's in terms of n. I haven't said, okay, I haven't determined what order derivative I want. And I've got, I'm using a symmetric difference. So I've got 1 to the left, and that's multiplied by alpha 1. I've got the central one, which is multiplied by alpha 2. And I've got the one to the right, which is multiplied by alpha 3. So alpha 1, alpha 2, alpha 3 are my coefficients. I want to be able to calculate the values of these coefficients. That will depend upon 2 things. One, what is the order of accuracy I would require? And 2, what's the order of the derivative I'm trying to approximate? Okay, so the first thing is you write down your finite difference in terms of some neighboring nodes and some coefficients. What we then do is we replace ux minus h and ux plus h with the Taylor series expansion of the required order of accuracy. Okay, so if you want a second order accurate, you replace them with second order Taylor series. If you want 4th order, you replace them with 4th order Taylor series. Then you factorize out any terms involving u. Okay, so we do a bit of algebra and we factorize out u terms. So you'll have some terms multiplied by u, some terms multiplied by ux, and some terms multiplied by uxx. Okay, the coefficients of the u terms should all be 0 apart from that derivative you're trying to approximate. And then from that, we form a systems of equations in terms of alpha and solve. Okay, so let's go through an example. Okay, so I'm going to use this example from the previous slide. I have 3 coefficients, alpha 1, alpha 2, alpha 3. I've got a symmetric difference. So I'm going 1 to the left, 1's in the center, and 1 to the right. So what I do is I replace the 1 to the left and 1 to the right by Taylor series expansions. And I've chosen second order here. So replace those with second order Taylor series expansions. So instead of ux minus h, I've just replaced it by this thing in the square bracket. So the next step is to factorize out the u terms. Okay, so what we got? Well, if we first look at the ux, okay, I've got alpha 1 times ux here. I've got alpha 2 times ux, and I've got alpha 3 times ux. Okay, so in all, I've got alpha 1 plus alpha 2 plus alpha 3 multiplied by ux. So that's that term done. What about the derivative of u? Okay, well here I've got minus alpha 1 times h. Here I've got no derivative of u at all. And here I've got plus alpha 3 times h. Okay, so I've written it in this form. So I've got minus alpha 1 times h plus alpha 3 times h. As you can see, h is just factorized out, so it's a common factor. And finally, what about the second derivative? Well, here I've got alpha 1 times h squared over 2. Here I haven't got a second derivative. And here I've got alpha 3 times h squared over 2 again. Okay, so I've taken a half out there. Alpha 1 plus alpha 3 times h squared u(x). Okay, so all I've done in this step is to take this and factorize out the u, the derivatives of u, and that gives me that. Okay, from this, we now decide, okay, which derivative do we want to approximate? Okay, so let's say we want to approximate the first order derivative. So, okay, thing on the left is now a first order derivative. I need to make sure that the left-hand side here equals this right-hand side. So to do so, there's nothing on the left-hand side which involves u of x. So therefore, alpha 1, alpha 2, and alpha 3 should be equal to 0. The second term involves ux, and I want one lot of ux. So I need minus alpha 1 plus alpha 3 times h to be 1. Okay. This is where this comes from. If minus alpha 1 plus alpha 3, if that's equal to 1 over h, I have 1 over h times h, which gives me 1. And finally, there's no second order derivative this side, but we have this here. So I need to make sure that half alpha 1 plus alpha 2 is equal to 0. And therefore, if alpha 1 plus alpha 3, if these two are equal to 0, then that term is all equal to 0. So I need the solution to this system here. Linear system, I need that solution. Quite easy to solve. Okay, if I solve that, I get alpha 1 is minus 1 over 2h, alpha 2 would be 0, and alpha 3 is 1 over 2h. So what we have is we have minus 1 over 2h times the node to the left plus 1 over 2h times the node to the right. And I could put those together, which gives me this, which is the central difference approximation. That's another way of deriving the central difference approximation. It's more complicated, I grant you, but when we look at higher order derivatives, we could easily derive them using this method. Okay. Right, I'm going to go through a worked example now. I think you've listened to me talk without doing anything at all for a while. So I'm going to go for a worked example, and I'm going to derive the second order symmetric finite difference approximation of uxx. Okay, so I'm going to move over to the visualizer now. Okay, so what we're driving is that autofocus? Does that look okay? I'll zoom in a bit more. That's a bit. Okay, that's what I want to drive. I want to derive a finite difference approximation of this. Okay, and I think on the slide I've taken it off now, but I think I asked for essential. So what I'm going to have is I'm going to have some coefficient multiplied by the left hand node, or the one to the left, some coefficient multiplied by the central node, and another coefficient multiplied by the node to the right. Alpha 1, alpha 2, and alpha 3 are my undetermined coefficients. That's what I want to find the value of. Okay, in doing so, I need the Taylor series. So I might as well write it down. So the Taylor series is ux plus h times the derivative of u plus h squared over 2 times the second derivative. Okay, so that's second order Taylor series. Also write down the backwards Taylor series. So all we do is substitute minus h in place of h. Okay, so the top line is my finite difference approximation, but I don't know what alpha 1, alpha 2, or alpha 3 is. Lines 2 and 3 are Taylor series, so just second order Taylor. Okay, so what I'm going to do is I'm going to plug these two into the top line. So what we have is alpha 1, and that's multiplied by the third line, so the backwards Taylor series. That's ux minus hux, the derivative of u, sorry, plus h squared over 2, second derivative of u. Okay, so that's the one on the left done. The central node is just alpha 2 times ux. I'm going to have to go on to a different line here, but the node on the right is then alpha 3, and that's just multiplied by the forward Taylor series. Okay, so all we've done there, just substitute the Taylor series into that equation. Next step, we need to factorize this. Okay, what I want is I want something times ux, something times the first derivative of ux, and something times the second derivative of ux. Okay, so what we have is I'm going to have something times ux, okay, plus something times the derivative of ux plus something times the second derivative of ux. Okay, so to do this, I just look at what is ux being multiplied by. Okay, here, ux is multiplied by alpha 1. I'm going to put that there. Here, ux is being multiplied by alpha 2. So I've got another ux which is multiplied by alpha 2. And finally, it's multiplied by alpha 3. Okay, so that's factorising that term. So there's 3 of them. For the first derivative, we have alpha 1 times minus h. We've got nothing here because we've got no first derivative. And here we got plus alpha 3 times h. Okay, so I'm going to say we've got minus alpha 1 plus alpha 3. And I've taken the h outside because both of these are multiplied by h. So just to simplify the algebra. Okay, what about a second derivative? Okay, here I've got alpha 1 times h squared over 2. Here I've got nothing. And here I've got alpha 3 times h squared over 2. So I've got alpha 1 plus alpha 3. That's all multiplied by h squared over 2. Okay, remember, what we're looking for is the second derivative. Okay, so I want this to be equal to 0, and I want minus alpha 1 plus alpha 3 to be equal to 0. Okay, so I want this term, all of these to be equal to 0. So I have alpha 1 plus alpha 2 plus alpha 3. Okay, that should be equal to 0. Minus alpha 1 plus alpha 3 should also be equal to 0. And finally, we want this term, the term which is multiplied by uxx, to be 1. So what I want here is for alpha 1 plus alpha 3 to be equal to 2 over h squared. Because if alpha 1 and alpha 3 are equal to 2 over h squared, okay, I've got 2 over h squared multiplied by h squared over 2. That's just 1. Okay, so if this is satisfied, if this system down here is satisfied, we'll have uxx equals uxx. And we'll have our undetermined coefficients. Okay, let's solve this. Quite a simple. It's quite a simple system. If I add 2 to 3, equation 2 plus equation 3. Okay, we have those cancel out. 2 alpha 3 equals 2 over h squared. So this must imply alpha 3 is 1 over h squared. Okay. So add that, gets rid of the alpha 1s. 2 alpha 3 equals 2 over h squared. Therefore, alpha 3 must be 1 over h squared. Okay, well, from equation 2, minus alpha 1 plus alpha 3 is 0. So therefore, alpha 1 must be the same as alpha 3. So alpha 1 must also be 1 over h squared. So I've got alpha 1, I've got alpha 3. And in the first equation, all 3 of them added together equals 0. So from equation 1, it must mean that alpha 2 is minus 2 over h squared. So I've solved my undetermined coefficients. I know what those coefficients are. Okay, so I'm just going to scroll down a bit. Now, we started with this first line. I didn't know what alpha 1, alpha 2, alpha 3 are. But if we use second order differences, second order Taylor series, I now know what alpha 1, alpha 2, and alpha 3 is. So in that case, I can write my finite difference approximation in terms of, okay, alpha 1 was 1 over h squared. And that was multiplied by x minus h. Alpha 2 is minus 2 over h squared, sorry. So that's multiplied by ux. And finally, alpha 3 was 1 over h squared. and that was multiplied by ux plus h. Okay, I could tidy that up a bit. Notice they're all over h squared. Okay, since they're all over h squared, I can write, okay, minus 2 over ux plus ux plus h, all over h squared. And that's what we had earlier. We derived that earlier using the other method, the method of using lower order derivatives. So this is derived the same method, but just using a different approach. This undetermined coefficients approach can be used for any order. Okay, if you're doing fourth order, you'll end up with a 4x4 system of linear equations to solve. Fifth order will be 5x5. Okay. Okay, it's a neat and it's a general method that you don't have to mess about with lower order derivatives at all. It should all, if done correctly, it should always give you the correct finite difference approximation. Okay, I'll be scanning this document. I'll be scanning this what I've done on the visualizer and putting it on Moodle. So don't worry if you haven't got it all down exactly. I'll be scanning that in. Okay. All right, I'm just going to go back to the slides now for a sec. Okay, so that was a worked example on deriving second order symmetric difference. Okay. Another neat example is if we do a one-sided difference. Okay, everything we've done so far, central, symmetric, and first order backwards and forwards. Okay, one thing we can do now is a one-sided. Now, we want to calculate a derivative at the point x. What if we haven't got any information of nodes to the left, but we have information of nodes to the right? So therefore, I could have a difference formulae that use our x node, the node 1 step to the right, and the node 2 steps to the right. Okay, so I haven't stepped anything backwards. I haven't gone backwards at all. Okay, this is what we call a one-sided difference. Useful near where you're at the boundary of the domain. Okay, to do this, we need the Taylor series expansion of 1 plus 2h. So the Taylor series I've been using so far has just been x plus h. So now we need it for x plus 2h. So if we substitute 2h in place of h, okay, this is what we get. This is the second order Taylor series where we're stepping 2 steps to the right. Okay, so we had ux plus h derivative, first derivative, so therefore it's 2h, plus h squared over 2. Now h squared over 2, if I have 2h, that's 4h squared over 2. 4h squared over 2 is just 2h squared. Okay. So now what I do, doing the same process, if I substitute in that's the standard Taylor series, second order there. Okay, and this is the one I've just derived, this one up here. So if I substitute those in and factorize as I have been doing, so it's exactly the same, but I just come up with a different coefficients here and here. Okay, so plug in the Taylor series, factorize. This is the system you come up with. We have to solve this system for alpha 1, alpha 2, and alpha 3. And if you do that, you'll get these coefficients. I'm going through this quite quickly because it's I'm not expecting you to actually have solved this just by looking at it, but just take my word for it, but these are the solutions. Okay, so plug it back in, and we have the one-sided finite difference approximation. Okay, so the method of undetermined coefficients is quite useful because it allows us to sort of mess about with the shape of our finite difference formulae. And so this one-sided, let's say this is used at the left-hand boundary where we got no further information, anything outside the boundary. So that's useful there. Okay, so what I'm going to do now is I'm going to do have a look at these in a bit of a practical sense. So I'm going to just switch to Matlab, which I know you all love. Okay, and I'm going to have a look at calculating these finite difference approximation of e to the x. Okay, so this is what I'm going to do is by the way, hopefully this is being recorded, so if you need to sort of go back and play this, all of this will be recorded. You'll have to fast forward 55 minutes to get to this point there. Okay. Right, so what I'm going to do now is I'm going to write a Matlab file that calculates first, second, and fourth order difference approximations of e to the x. And I want to show you how we can do that and have a bit of an analysis of the error. And this is quite similar to your first tutorial lab sheet, which you'll be doing next week. So what I'm doing now is kind of showing you how to do the tutorial stuff next week. Okay, so what I'm going to do is start off. Can you all see that, by the way? Is that sort of big enough for you at the back? You can see it. Okay. Okay. Something by habit I do. I just clear workspaces, make sure there's nothing left in the memory from a previous file. Okay. What I'm going to do is I'm going to calculate. Let's say x equals 1. Okay, I'm going to calculate a derivative of e to the x at x equals 1. What's that going to be? What's the derivative of e to the x? E. What's e to the 1? 2.7818, blah, blah, blah. You know that. Okay, so that's what I should be getting. So I know what the actual solution should be. I'm going to show how we can approximate that using differences. Okay, I'm going to use a step length of 1/2. Okay, quite a large step length. Normally step lengths are in the region of about 100th or something like that. But I'm going to use step length of 1/2. Okay, so define the variables. Calculate finite difference approximations. Start approximation wrong there, but can't be bothered. Okay, so the forward difference approximation, I'm going to call it forward. Okay, that is, if I let's say what function I'm doing. Okay, so it's the exponential function one step to the right minus current node. Okay, so we want to calculate the finite difference approximation at e to the x. Okay, so we take a step to the right and subtract the e to the x node. And that's all divided by h. Okay, so that's the forward difference approximation. Let's see what happens when I run that. I'm just going to go back. There you are. My forward difference is 3.5268. We're looking for about 2.7818. So you can see it's quite a poor approximation. What about the backwards difference? Is that going to give me anything better? Let's calculate the backward difference. Okay, so there's a backward difference. So instead of going forward, we take e to the x and e to the x minus h. Okay, run that. 2.1391. Okay, so it's still not very good. We're looking for 2.7818. What about central? Okay, so let's try a central difference. So in this case, we take a step to the right and subtract the step to the left. Okay, let's see what that gives us. Oh, forgot to divide this time by h squared, isn't it? Anybody spot an error? Oh, it's 2/8, sorry. That's a second order derivative. Yeah, so as you can see there, made an error. Even though it gave me an output, I had to sort of like validate the program. Okay, so I got 2.833. Closer, a lot closer than my first order derivatives. What I'm going to do now is calculate a fourth order. Now, I haven't shown you this yet because it's your tutorial task for next week. But the fourth order I'm going to call it fourth, is e to the x minus 2h minus 8 times e to the x minus h plus 8 times e to the x plus h minus e to the x plus 2 times h. Okay, and that's all over 12h. Okay. You're going to be expected to derive that in the tutorials next week. So I want you to derive that using using undetermined coefficients. Okay, let's have a look, see what that gives us. 2.7124. Okay, I'm getting closer and closer. As I'm up in the order, I'm getting closer and closer. Okay, okay, so that's using h of a half. Okay, what happens as I reduce h? So what I'm going to do now is I'm going to change this program, so I'm going to loop for different values of h. Okay, so what I'm going to do is I'm going to put for loop in, and let's go for 5 different values of h. Okay. Okay, so I'm going to loop for 5 different values of h, and what I'm going to do is I'm going to halve h each time. So I'm going to start with h is a half. I'm going to calculate h. And h is going to be equal to 2 to the power minus I. Okay, so just to explain this, when I is 1, 2 to the power minus 1 is a half. When I is 2, 2 to the power minus 2 is a quarter. Then it'll be an eighth, then it'll be a 16th, then it'll be a 32. Okay, so every time I step through, h is going to be a half of what it was previously. Okay. What I also want is I want to keep track of the different values of h's I've used. Okay, so I'm going to create an array. Okay, so the ith value of h is going to be my current step length. Unfortunately, that means all of these h's in here are all going to have to be changed to that. Okay, so a quick way of doing that, if I do a find and replace. So if I find h and replace it with hi. Okay, so find next. This is a little bit of a trick. If I just keep clicking replace, and it will replace all those. Okay, don't need that one anymore, so I'm going to delete that. Okay, so that's going to calculate the forward, backward, central, and fourth order difference of using different values as a step. Okay, I've just noticed it's changed that h there to I, but that's good because I need that anyway. So I'm going to just change all these others. So if I was to run this program, let's run it. Okay, it's run. Okay, there we have. Oh, I forgot to just take off that semicolon if we run it again. Okay, so if I check what the backward difference looks like. So this one is when h is a half. This one is when h is a quarter, an eighth, 16th, a 32. So as you can see, as the step length decreases, the accuracy is increasing. It's not increasing very fast, but it is increasing. What about the central difference? Okay, so again, there's the same h is a half, h is a quarter, an eighth, 16th, 32. When we get down to this one, we're actually not that far off. Okay, so this one actually converges to the solution faster. What about the fourth order? Oh, got fourth wrong. There you go. Okay, well, if we're looking to 4 decimal places, but by the time we get to h is an eighth, we're already correct to 4 decimal places. Okay, so that's a sort of rudimentary look at it. Let's change the program so we can actually tabulate how good, tabulate our errors. Okay, so what I'm going to do here is I'm going to calculate the errors. Now, the exact solution is the exponent e to the 1. Okay, so what I'm going to do is I'm going to calculate the error for the forward difference, which is the absolute error between the exact and forward. Okay, so this will calculate what the absolute error is between the exact solution and our approximation. What I'm going to do, I'm going to do the same for the backward, central, and fourth. Okay, so I'm using a bit of a copy and paste trickery. Put it back, call it central, and fourth. Okay, so instead of forward, we had backward. Instead of forward, we had central. And instead of forward, we have fourth. Okay. So what this has done is taking my approximations, I've calculated the errors, and I've called here. So what I want to do now is tabulate these. I want to show them on the command window. So output errors. I'm going to use an F statement. Okay, if you can see that down there. Print F. Okay, what am I got? I'm going to start off with outputting H. So let's say 8.6 F. But 8.6 F. So I need 4 of these for each one of the. So I've got forward, backward, central, and fourth. So then I've got error 4, error back, error central, and error 4. Oh, I forgot the 8 and 9. Yeah, I forgot the 8. Right. Okay, it hasn't beeped at me, so oh yes it has. Input of argument type character. Ah yes, well spotted. There we go. So those are the errors. Okay, so the first column is your H's. Second column is forward, backward, central, fourth order. Okay, I want to tidy that up a bit because I don't know what the columns mean. So before I go into that for loop, I'm just going to output some column headings. And this is a bit of a trial and error sort of thing. You got H, you got forward, backward, central, and fourth. Oh, I need a and what you can do is you can sort of put in spaces where you need it, just to make it look better, but that gives it enough. Okay, so that's the absolute errors for each of those approximations. The final thing I want to show you is the idea of a log-log plot. Have you ever heard of a log scale plot? Okay. If you recall, just going to go back to the visualizer for a second. Our errors, I'm going to call it errors E, are of this form. Okay, error E is of a form, or the behavior of the error E is of the form some number C times h to the power n. N is the order of our method. Okay, so what I want to find out is if I know what E is, and I've just calculated the errors, I know what H is, because H started at a half, then it was a quarter, then it was an eighth. What is this N? Okay, so what I could do is I can take logs of both sides. Okay, I'm going to drop the C actually. The C is going to disappear because it's just some number. Okay, C is just some number. It's not going to affect the behavior. So I've got log E equals log h to the n. I can bring n outside the log by laws of logarithms. So I'll have log E equals n log h. So what I can do is I can graph e, the log of the error, against the log of the step length. I could do that. That will show me a straight line. This is a linear relationship between e and h. Between log e and log h is a linear relationship. Furthermore, I can estimate what my order is. Okay, the order is approximately the change in the log of the error divided by the change in the log of the h. Okay, so that's why what we tend to do when we're looking at errors, we tend to plot them in a log-log scale, because it allows us to approximate what my order of the method is. If you don't know the order of a method, this will approximate it. Okay, so let's mess about with the Matlab script just to do that. So if we go to the Matlab, okay, so after I calculated everything, a log-log plot in Matlab, okay, for those of you who don't know, it's just log-log. Okay, so instead of plot, I write log-log. And it wants an x. It wants x against y. So my x's are going to be h, and my y's, let's take the error for the fourth order to start. Sorry, forward. Sorry? Is that right? Okay, let's see what happens there. There we go. Right. That's the output. I'm just going to blow that up a bit. Okay, so actually, I just make that a bit clearer. There we go. Okay, so h starts off at the far right as a half. So on the point on the far right, that's when h is a half. Every step to the left, we're halving h. But notice, because it's a log scale, the differences between them are constant because I've taken a log scale. You know it's a log scale by these tick marks down here. So this is a log scale. And the vertical axis is the error. Okay, again, it's a log scale. So just to tart up the thing a bit better, it's going to say the x label is log of h. Give it a bit of a bigger font size. I'm going to do the same with the y label. Okay, so on the bottom, we've got the log of h. On this axis, we've got log of error. Okay, that's a first order method. What about a second order method? So on the same plot, I'm going to plot the central difference errors. Okay, so here we go. Okay, so this is the central difference errors. One thing I want to notice here is the slope of the red line is steeper than the slope of the blue line. Now the slope is what gives us the order of the method. So what it can actually do is approximate what the slope of the blue line is and what the slope of the red line is. Okay, so to do that, okay, so I'm going to approximate the orders. Okay, so my estimate of the first, the forward. Okay, so FOR stands for forward. I'm going to estimate what the order of that method is. Okay, so we have the log of the error at the first, using the first h, okay, minus the log of the error using the fifth h. Okay, so the first, this one is the least accurate. This one was using h of 1/32. So this one would be more accurate. So that's a change in accuracy. So log of the least accurate minus log of the most accurate, that's a change in accuracy. And I'm going to divide that by log of the largest h minus log of the smallest h. Okay. Let's run on that. Oh, doesn't like something. What have we got there? Did I call it forward error? Error 4. So I called it error 4. Okay, so it's estimated it. The error, according to these errors, it's estimated it, but this has got an order of 1.105. There, it should be 1. Fairly close. Let's do the same with the central difference. So I'm just going to sort of copy and paste that instead of, so that's essential. So instead of error 4, I've got error central. From that, should be 2, it's 2.0045. Okay, so error analysis like this, so with this log-log plot, it allows us to estimate what the error or what the order is, the method you're using. So if you know what the actual solution would be, you can compare it, plot it on a log-log scale. The slope of these lines should give you the order of the method. Lastly, what I'm going to just do is plot the 4th order as well, just to show you. So if I do a log-log plot of the 4th order errors, okay, so you can see steepest hill. So this has got a shallow line because it's 1st order. This has got a steeper line because it's 2nd, but this one's steeper still. Now that should be a 4th order method. Let's see what our estimate gives us. Okay. So I'm going to do the same estimate, but this time for the 4th order. So check errors against the 4th order, giving us 4.0107. Okay, so it's estimated, but the 1st order method is of order 1.0589. The 2nd one is 2.0045, and the 4th one is 4.107. So it's close. It's not bang on, okay, but it gives us a kind of guide to what the orders of the method are. Okay, so in the tutorials next week, I've got a lab sheet which will do this sort of thing, but for a cosine function. I want you to get used to the idea of approximating derivatives using these finite differences, and also a bit of error analysis as well. Okay, are there any questions regarding what I spoke about in the last hour and 20? Okay, is it straightforward, or are you a bit sort of freaked out by it, or is it okay? You've been very quiet. Is it the Matlab which is the hard bit? Okay. Hopefully this lecture has been recorded. Fingers crossed. If it isn't, what I might do is make a screencast of doing this sort of thing, and to help you. Okay. I do appreciate the Matlab would be the hard thing. What I would say about Matlab is I'll tend to give you skeletal code, or I'll tend to give you some code which you just have to change. Okay, so in the notes there won't be this code, but for all the other stuff there is code. So hopefully the Matlab won't be too much of a problem. Okay, I think that finished in about 10 minutes early today. So next week I'm going to be looking at building a finite difference scheme from scratch. Okay, so we're going to have a look at solving our first PDE. So that'll be next week.